somewhere between Mars and Jupiter, drifting in a belt of shattered rock and frozen debris, there is a world that should not be round. It is not a planet. It is not a moon. It has no atmosphere, no magnetic field, no warmth of any kind. Its surface temperature hovers around negative 170 degrees Celsius. Sunlight reaches it, but only barely, a pale reminder that a star exists somewhere out there. And yet, against every expectation, against every model that physicists and planetary scientists have built over centuries, this object has done something that objects its size are not supposed to do. It has pulled itself into a sphere. Its name is Hygiea, and almost no one has ever heard of it. In the grand census of our solar system, there are 8 planets. Most people can name them. There are 5 officially recognized dwarf planets, and most people can name at least one, Pluto. There are hundreds of moons, thousands of comets, and millions of asteroids. But in that crowded middle ground, in that chaotic belt of rubble that separates the inner rocky planets from the outer gas giants, one object has been quietly defying classification for more than 170 years. It was discovered in 1849. It was measured, catalogued, and largely forgotten. For most of modern astronomy, Hygiea was just another asteroid. The 4th largest in the belt, yes, but still just a rock, a lump, a leftover from the earliest days of the solar system. Interesting only to specialists. Then, in 2019, a team of astronomers pointed one of the most powerful telescopes on Earth directly at it, and what they saw changed everything. Hygiea is round. Not roughly round, not potato-shaped like most asteroids, not elongated or irregular or cratered into asymmetry. Round, spherical, the kind of shape that only forms when an object has enough mass for its own gravity to crush it into equilibrium. The kind of shape that, according to the rules set by the International Astronomical Union, qualifies an object for one of the most contested labels in modern science, dwarf planet. If Hygiea is reclassified, it would become the smallest dwarf planet in the solar system, smaller than Pluto, smaller than Eris, smaller than Ceres, the current reigning champion of the asteroid belt, and it would force astronomers to ask a question they have been avoiding for almost 2 decades. Where, exactly, do we draw the line between a rock and a world? But the shape is only the beginning of the mystery. When the astronomers examined Hygiea's surface with the Very Large Telescope's sphere instrument, an adaptive optics system so precise it can cancel out the blurring of Earth's atmosphere in real time, they expected to find something specific, something obvious, a crater. Not just any crater, but a massive one. Hygiea is the largest member of a family. In asteroid science, a family is a group of objects that share similar orbits and compositions. And the reason they share those traits is that they were all once part of the same body. Something enormous struck the original Hygiea billions of years ago, and the collision was so violent that it blasted nearly 7,000 fragments into space, scattering debris across the belt. The Hygiea family is one of the largest asteroid families in the solar system. The violence required to produce it would have left an unmistakable scar on whatever remained. A basin hundreds of kilometers wide, a wound in the rock that would still be visible after 4 billion years. They found nothing. No giant crater, no basin, no scar. The surface of Hygiea is remarkably smooth and featureless at the resolution they could achieve, which means one of 2 things. Either the collision was so catastrophic that it completely shattered the original body, and the fragments reassembled under their own gravity into the sphere we see today. A process that would make Hygiea not a survivor of a cosmic impact, but a resurrection, or something else happened. Something we do not yet understand. By the end of tonight, you are going to understand why a single round object, less than 450 kilometers across, drifting in the cold emptiness between Mars and Jupiter, has quietly become one of the most important puzzles in planetary science. You are going to see how its existence challenges our definitions, our models, and our assumptions about what it means to be a world. And you are going to confront a question that has no comfortable answer. If Hygiea is a dwarf planet, how many more are out there, hiding in the dark, waiting to be seen? Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, Let us begin. To understand why Hygiea matters, you first have to understand the place where it lives. And that place, the asteroid belt, is nothing like what most people imagine. Close your eyes and picture the asteroid belt. If you grew up watching science fiction, you are probably imagining a dense field of tumbling boulders, so thick that a spaceship would have to weave and dodge just to pass through. Rocks smashing into each other, constant collisions, a cosmic minefield. That image is burned into popular culture, and it is almost entirely wrong. The real asteroid belt is empty. Staggeringly, oppressively empty. If you were standing on one asteroid and looking around, the nearest one would likely be so far away that you could not see it with the naked eye. The average distance between asteroids in the belt is roughly 1 million kilometers. That is almost 3 times the distance from the Earth to the Moon. You could fly a spacecraft through the belt in a straight line, and the odds of hitting anything are so small that NASA does not even bother to calculate avoidance trajectories. Every spacecraft humanity has ever sent to the outer solar system, Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, Galileo, Cassini, New Horizons, Juno, has passed through the asteroid belt without incident, not because they were lucky, but because there is simply nothing there to hit. And yet, despite all that emptiness, the belt contains something staggering. Estimates suggest there are between 1 and 2 million asteroids larger than 1 kilometer in diameter. Hundreds of millions more are smaller than that. In total, the belt holds enough rock and metal and ice to build. Well, that is where it gets humbling. If you gathered every single asteroid in the belt and compressed them into a single body, the resulting object would have roughly 4% of the mass of Earth's moon. It would not even be large enough to hold an atmosphere. The entire asteroid belt, all those millions of objects spanning a region of space, more than 250 million kilometers wide, contains less material than a single modest moon. This is the first clue that something dramatic happened here. Something went wrong. The asteroid belt is not a collection of debris from a planet that exploded. That was the old theory, popular in the 19th century, and it has a certain dramatic appeal. But it is incorrect. The belt is something more tragic. It is the graveyard of a planet that was never born. 4.5 billion years ago, when the solar system was still forming from a spinning disk of gas and dust around the young sun, the region between Mars and Jupiter should have produced a planet. There was enough material, the conditions were right, but something interfered, something massive and gravitationally overwhelming was forming nearby, and its influence was catastrophic. Jupiter. Jupiter, even in its infancy, was enormous. As it grew, its gravitational pull reached across the gap between its orbit and Mars, stirring the material in the belt, accelerating it, perturbing the orbits of the forming planetesimals, the building blocks that should have assembled into a world. Instead of gently colliding and sticking together, the way they did closer to the Sun, where Mercury, Venus, Earth, and Mars formed, the planetesimals in the belt region smashed into each other at speeds too high for accretion. They shattered instead of merging. Jupiter's gravity turned the belt from a nursery into a demolition zone. The planet that should have formed there was never allowed to exist. What remains is a population of survivors, fragments, relics from the solar system's earliest era, preserved in the deep freeze of space like fossils in amber. And among those relics, 4 objects stand above the rest. The largest is Ceres. At 940 kilometers in diameter, Ceres is mass enough to have pulled itself into a nearly perfect sphere. It contains roughly 1/3 of the total mass of the entire asteroid belt. In 2006, when the International Astronomical Union created the category of dwarf planet, the same decision that famously stripped Pluto of its planetary status, Ceres was immediately included. It orbits the Sun. It is round. It has not cleared its orbital neighborhood. It is a dwarf planet. The second largest is Vesta, at roughly 525 kilometers across. Vesta is an irregular battered world with a giant impact basin near its south pole called Reassembled, one of the largest craters in the solar system. Vesta is not round enough to qualify as a dwarf planet. Its shape is distinctly oblate, scarred and lumpy. But it is differentiated, meaning it has a core, a mantle, and a crust, just like Earth. It is in a sense a failed planet, a protoplanet that almost made it. Third comes Pallas, roughly 512 kilometers across. Pallas has a heavily cratered, irregular shape and one of the most highly inclined orbits in the belt. It tilts at nearly 35 degrees relative to the main plane of the solar system, which makes it difficult to study and even more difficult to visit with a spacecraft. Pallas is fascinating but has been largely overlooked by major missions. And then there is Hygiea, the fourth, the quiet one. With a diameter of approximately 434 kilometers, Hygiea is significantly smaller than Ceres, Vesta, or Pallas. It orbits in the outer part of the main belt, roughly 3.14 astronomical units from the Sun, meaning it is about 3 times farther from the Sun than Earth is. At that distance, sunlight is dim, temperatures are brutal, the surface is coated in dark, carbon-rich material that reflects very little light, giving Hygiea an albedo, a reflectivity, of only about 6%. For comparison, Earth's moon reflects about 12% of the sunlight that hits it. Hygiea reflects roughly half that. It is one of the darkest large objects in the inner solar system. This darkness made it difficult to study. For more than a century and a half after its discovery, Hygiea remained a mystery wrapped in shadow. Astronomers knew its orbit. They knew its approximate size. They knew it was the namesake of a large asteroid family. But its shape, its surface features, its internal structure, all of these were essentially unknown. The story of Hygiea's discovery begins in the city of Naples in the year 1849. Italy was in political turmoil. The revolutions of 1848 had swept across Europe, and the Kingdom of the Two Sicilies was no exception. But in the midst of that upheaval, a young astronomer named Annibale de Gasparis was doing something extraordinary. Working at the Capodimonte Observatory, perched on a hill above the city, de Gasparis was systematically hunting for new objects in the night sky. He had already discovered the asteroid Hygiea's predecessor in the catalogues, Asteroid 9, Metis, and he was determined to find more. On the 17th of April, 1849, de Gasparis found Hygiea. He named it after the Greek goddess of health, Hygiea, daughter of Asclepius, the god of medicine. The naming was conventional for the time. Asteroids were given mythological names as a matter of course. But there is a quiet irony in the choice. Hygiea, in Greek mythology, was associated with prevention, with cleanliness, with the preservation of well-being. The asteroid that bears her name has spent more than 4 billion years in one of the most violent neighborhoods in the solar system, surviving collisions that destroyed entire worlds. De Gasparis was awarded the Gold Medal of the Royal Astronomical Society for his asteroid discoveries, but Hygiea itself received little attention. It was dim, it was far away. It was, to all appearances, just another rock. For the next 170 years, that assessment barely changed. Hygiea appeared in catalogues, in orbit calculations, in statistical surveys of the asteroid belt. It was measured with photometry, brightness measurements that could provide rough estimates of its size and rotation period. Those measurements suggested Hygiea was large, dark, and slow spinning, rotating once every 27.6 hours. It was classified as a C-type asteroid, meaning its composition was consistent with carbonaceous chondrite meteorites, the most primitive material in the solar system. It was interesting, in a quiet sort of way, but it was not special. What was special was its family. The Hygiea family, sometimes called the Hygeian family, is one of the most prominent asteroid families in the outer main belt. It consists of nearly 7,000 known members, all sharing similar orbital elements, similar semi-major axes, similar eccentricities, similar inclinations, and similar spectral properties. This similarity is the fingerprint of a shared origin. At some point in the distant past, a single large body was struck by another object, and the collision was violent enough to produce thousands of fragments that spread out along similar orbits. Over billions of years, those fragments drifted apart, but they still carry the signature of that ancient catastrophe. The size of the Hygiea family tells you something about the scale of the impact. To produce nearly 7,000 fragments, many of them kilometers across, the collision must have been extraordinary. Computer simulations suggest the impactor, the object that struck the original Hygiea, was somewhere between 75 and 150 kilometers in diameter. That is not a small rock. That is a minor world in its own right. something the size of a large moon, slamming into Hygiea at speeds of several kilometers per second. The energy released would have been almost incomprehensible. Billions of times the energy of the largest nuclear weapon ever detonated, enough to melt rock, vaporize metal, and reshape the entire object. And here is where the story begins to diverge from expectation. When an impact that violent strikes an asteroid, it should leave a mark, a very obvious mark. Vesta, which experienced a similar catastrophic collision, has the Reassembled Basin, a crater nearly 500 kilometers across, so large that its central peak rises 22 kilometers above the crater floor, making it one of the tallest mountains in the solar system. The impact excavated roughly 1% of Vesta's total volume and blasted fragments all the way to Earth, where they landed as a specific type of meteorite called Hygiea meteorites. The scar is obvious. It dominates Vesta's southern hemisphere. So when astronomers began seriously considering Hygiea's family, they naturally expected to find something similar. A giant crater, a basin, some unmistakable evidence of the blow that created thousands of fragments. The logic was simple. The bigger the family, the bigger the impact, the bigger the crater. The Hygiea family is enormous. The crater should be enormous too. For decades, no one could check. Hygiea was too far away and too dark for ground-based telescopes to resolve any surface features. The Hubble Space Telescope could provide slightly better images, but not enough to settle the question. No spacecraft had ever visited Hygiea. No close-up photographs existed. The asteroid remained, as it had been since 1849, a point of light with a name. Then came SPARE. SPARE stands for Spectropolarimetric High-Contrast Exoplanet Research. It is an instrument mounted on the Very Large Telescope at the European Southern Observatory's Paranal Observatory in Chile, high in the Atacama Desert, one of the driest places on Earth. The air above Paranal is so still and dry that it provides some of the best astronomical seeing conditions in the world. SPARE was designed primarily to directly image exoplanets, to block out the light of a star and photograph the faint worlds orbiting it. But its adaptive optics system, which uses a deformable mirror to correct for atmospheric turbulence hundreds of times per second, also makes it capable of resolving the shapes of small solar system objects with unprecedented clarity. In 2017 and 2018, a team led by astronomer Pierre Vernazza of the Laboratoire d'Astrophysique de Marseille used SPARE to observe Hygiea across multiple viewing angles as it rotated. They captured images at different times during Hygiea's roughly 27.5-hour rotation period, building up a three-dimensional model of its shape from the silhouettes recorded at each angle. The technique is called disk-resolved imaging, and for an object as small and dark as Hygiea, it pushed SPARE to its limits. The results were published in the journal Nature Astronomy in late 2019, and they were not what anyone expected. Hygiea was round, not just roughly round, spherical. The measurements showed that Hygiea's shape was consistent with hydrostatic equilibrium, the state in which an object's gravity is strong enough to overcome the rigidity of its material and pull it into a sphere. The dimensions were striking. Hygiea's two primary axes differed by no more than about 10 kilometers. For an object 434 kilometers across, that represents a deviation from perfect sphericity of roughly 2%. That is more spherical than Ceres, more spherical than Vesta, more spherical than many moons, and there was no giant crater. The team searched the images carefully. They identified two relatively small craters, both less than 100 kilometers in diameter. But there was no basin comparable to Resolvia on Vesta, no giant scar, no obvious evidence of the cataclysmic impact that should have created the Hygiea family. The surface was smooth, the shape was round, and the implications were profound. Pierre Vernazza himself was quoted as saying that the discovery was truly surprising. The team had expected to find a large impact basin. Everyone had. The absence of such a basin, combined with the unexpected sphericity, pointed to a scenario that was far more dramatic than a simple cratering event. It suggested that the collision that created the Hygiea family did not just gouge out a chunk of the original body, it obliterated it completely. The impact was so catastrophic that it shattered the original Hygiea into thousands of pieces, dispersing them through the belt. And then, over time, most of those pieces, the ones that stayed close enough to the largest fragment, fell back together under their own mutual gravity. They reassembled, they reaccreted, and as they did, gravity did what gravity always does when enough mass is involved. It pulled the reassembled body into a sphere. Hygiea is not a survivor, it is a phoenix, a world that was destroyed and remade. And it is that remaking, that gravitational resurrection, that has turned a quiet, dark asteroid into one of the most provocative objects in the solar system. But here is the problem. The physics of this scenario raise as many questions as they answer. And the first of those questions is also the simplest and the hardest. How? How does an object this small, less than 500 kilometers across, pull itself into a sphere? Objects far larger than Hygiea are irregular. Pallas, which is roughly 80 kilometers wider, is not spherical. Vesta, which is nearly 100 kilometers wider still, is not spherical. What is different about Hygiea? What happened during that reassembly that allowed gravity to win? The answer, it turns out, depends on details that we are only beginning to understand. And those details connect Hygiea to a much larger debate, a debate that has been raging in planetary science since 2006, and that shows no sign of being settled. The debate over what it means to be a world. But before we arrive at that debate, there is more to Hygiea's neighborhood that demands attention. Because the asteroid belt is not just a junkyard, it is a laboratory. And the experiments it runs are written in the language of collisions. The physics of asteroid collisions is one of the most actively studied fields in planetary science, and for good reason. Collisions shaped the solar system. Every crater on every moon, every ring around, every gas giant, every meteorite that has ever fallen to Earth, all of them are products of impact. And the asteroid belt is where those impacts happen most frequently. Not because the belt is crowded, but because the objects in it are moving fast. Orbital velocities in the main belt range from about 15 to 25 kilometers per second. At those speeds, even a small impactor carries devastating energy. A rock the size of a football traveling at 20 kilometers per second packs more kinetic energy than a ton of TNT. Scale that up to an impactor 75 or 100 kilometers across, and you are dealing with energies that defy human intuition. To put it in perspective, imagine taking every nuclear weapon ever built by every nation on Earth, every warhead, every bomb, every test device, and detonating them all at once. The total energy released would be roughly 10 to the power of 19 joules. That is an enormous amount of energy. It is enough to level every city on the planet. But the collision that created the Hygiea family released energy roughly 1 billion times greater than that, enough to completely shatter a 400-kilometer-wide sphere of rock and send the fragments flying into space at several kilometers per second. And that collision was not unusual. Catastrophic disruptions of large asteroids have happened thousands of times over the past 4.5 billion years. The asteroid belt is littered with the evidence. Family after family after family, each one a tombstone marking the grave of a world that was. What makes Hygiea's story different is what happened after the destruction. Most catastrophic disruptions produce a largest remnant that is irregularly shaped. The fragments fall back together in a haphazard pile, held loosely by gravity but never smoothed into equilibrium. These are called rubble pile asteroids, and they are the most common type of large asteroid in the belt. Itokawa, the peanut-shaped asteroid visited by Japan's Hayabusa spacecraft in 2005, is a rubble pile. Bennu, the diamond-shaped asteroid sampled by NASA's OSIRIS-REx mission in 2020, is a rubble pile. Ryugu, visited by Hayabusa 2, is a rubble pile. They are loose, porous, structurally weak collections of gravel and boulders, held together by the faintest whisper of gravity. Hygiea should be a rubble pile too. By every expectation, by every model, by every precedent, it should be an irregular lump of reassembled debris. The fact that it is instead a smooth sphere is what transforms it from a curiosity into a profound scientific challenge. A challenge to the models, a challenge to the definitions, and a challenge to every assumption we have made about the boundary between rocks and worlds. There is one more detail that deepens this mystery. It concerns Hygiea's density. Based on estimates of its mass, derived from gravitational interactions with nearby asteroids and from the dynamics of the Hygiea family, and its volume. Calculated from the spare shape model, Hygiea has an estimated density of roughly 1.9 to 2.1 grams per cubic centimeter. For comparison, water has a density of 1 gram per cubic centimeter. Earth's average density is 5.5 grams per cubic centimeter. Solid rock typically ranges from 2.5 to 3 grams per cubic centimeter. Hygiea's density is lower than solid rock, which suggests one of two things. Either Hygiea contains a significant fraction of water ice or hydrated minerals, which would lower its bulk density, or Hygiea is porous, full of voids, gaps, and empty spaces left over from its reassembly, or both. A porous, icy interior would actually help explain the sphericity. Ice deforms more easily than silicate rock, especially over geological timescales. If Hygiea's interior contains enough ice or hydrated material, the effective strength of the body, its resistance to gravitational reshaping, would be lower than for a purely rocky object. This could lower the size threshold for hydrostatic equilibrium, potentially allowing a 400-kilometer object to achieve a shape that a purely rocky body of the same size could not. But this is still speculative. We do not know Hygiea's internal structure. We do not know the precise fraction of ice versus rock. We do not know how porous it is. Every estimate carries error bars large enough to drive a spacecraft through. And the only way to reduce those error bars, the only way to truly understand what Hygiea is, would be to go there, to send a probe, to orbit it, map it, measure its gravity field, analyze its composition, and determine once and for all whether this cold, dark, ancient object is a world or a pretender. No such mission has been approved. None is currently planned. Hygiea remains for now a question mark at the edge of our understanding, and that question mark is about to get much larger. On the 24th of August, 2006, the International Astronomical Union gathered in Prague for a vote that would change the map of the solar system. 2,400 astronomers from 75 countries packed into a conference hall to decide a question that might seem absurd on its face, but turned out to be one of the most contentious issues in modern science. What is a planet? The vote was not arbitrary, it was forced by a discovery. In 2005, a team led by Mike Brown at the California Institute of Technology had announced the discovery of an object beyond Neptune that appeared to be larger than Pluto. They called it Eris, after the Greek goddess of discord, and discord is exactly what it produced. If Pluto was a planet, then Eris had to be a planet too. And if Eris was a planet, then what about Makemake? What about Haumea? What about the dozens of other icy bodies being found in the Kuiper Belt? The solar system was suddenly filling up with potential planets, and astronomy had no definition to sort them. So the IAU created one. A planet, they decided, must satisfy 3 criteria. First, it must orbit the Sun. Second, it must have enough mass for its own gravity to pull it into a roughly round shape, a state called hydrostatic equilibrium. Third, it must have cleared the neighborhood around its orbit, meaning it must be the gravitationally dominant object in its orbital zone, having swept up or ejected most of the other material. Pluto met the first 2 criteria. It failed the third. The region of space Pluto inhabits, the Kuiper Belt, is full of other objects. Pluto has not cleared its neighborhood. It never will. So Pluto was reclassified as a dwarf planet, a new category that requires only the first 2 criteria, orbits the Sun, and is round. The decision was immediately controversial. Alan Stern, the principal investigator of the New Horizons mission that would later fly past Pluto, called it an embarrassment. He argued that the clearing the neighborhood criterion was flawed, because even Earth has not perfectly cleared its orbit. There are thousands of near-Earth asteroids. The counter-argument was that Earth is gravitationally dominant in its zone, in a way that Pluto simply is not. The debate raged in journals, at conferences, in popular media. It has never been fully resolved, but for all the fury over Pluto, almost no one noticed the quieter implication of the IAU's definition. The dwarf planet category was not just about Pluto. It was about any object that orbits the Sun and is round but has not cleared its orbit. At the time of the vote, only 3 objects were immediately classified as dwarf planets: Pluto, Eris, and Ceres. 2 more, Make and Hygiea were added shortly after, but the definition was open-ended. If another object could be shown to be in hydrostatic equilibrium, if it was round, it could qualify. No one was thinking about Hygiea, not yet. The concept of hydrostatic equilibrium is one of those ideas that sounds technical but is actually deeply intuitive. Imagine holding a handful of wet clay. If the ball of clay is small enough, you can shape it into anything: a cube, a pyramid, an irregular blob. The material is rigid enough to hold whatever form you give it. But now imagine that the ball of clay is enormous, the size of a house, the size of a mountain, the size of a continent. At some point, the weight of the material itself, the force of gravity pulling every part of the clay toward the center, overwhelms the strength of the clay. It does not matter what shape you try to make. Gravity will flatten it, smooth it, pull it into the shape that minimizes gravitational energy, which is always and everywhere a sphere. This is hydrostatic equilibrium. It is the reason planets are round. It is the reason stars are round. It is the reason very large moons are round. And the critical question, the question that determines whether an object is a world or a rock, is where the threshold lies. How much mass does an object need before gravity wins? The answer is not a single number. It depends on composition. An object made of ice reaches hydrostatic equilibrium at a smaller size than one made of solid iron. Because ice is weaker, it deforms more easily under pressure. It depends on temperature. A warm object is easier to deform than a cold one. It depends on internal structure. An object with a differentiated interior, a dense core surrounded by a lighter mantle, behaves differently from a homogeneous rubble pile. It depends on history. An object that formed slowly from gentle accretion may have a different shape from one that was smashed apart and reassembled. For rocky objects in the asteroid belt, the conventional wisdom held that the threshold for hydrostatic equilibrium was somewhere around 900 to 1,000 kilometers in diameter. Below that, gravity was not strong enough to overcome the strength of rock. Below that, objects would be irregular, cratered, lumpy. This was consistent with what astronomers observed. Sirius at 940 kilometers is round. Vesta at 525 kilometers is not. Pallas at 512 kilometers is not. Case closed. The line was somewhere between 500 and 900 kilometers. Hygiea at 434 kilometers was well below it. Too small, too weak, too rigid. Hygiea should be a potato, and it gets worse. The composition of Hygiea makes its sphericity even more puzzling. Hygiea is a C-type asteroid. Its surface, and presumably its interior, is rich in carbonaceous material, hydrated minerals, and possibly water ice. C-type asteroids are among the most primitive objects in the solar system, meaning they have not been significantly heated or altered since they formed. They are, in a sense, the raw ingredients of planet building, frozen in time, and those raw ingredients are not easy to deform. Carbonaceous chondrite material, the closest analogue we have in our meteorite collections, is a mixture of silicate minerals, organic compounds, and volatiles bound into a porous, crumbly matrix. It is not strong like iron, but it is not weak like ice. It falls somewhere in between, and at the temperatures found in the outer asteroid belt, -150 to -200 degrees Celsius, it becomes even more rigid. So the question becomes pointed. How did an object made of this material, only 434 kilometers across, in one of the coldest parts of the inner solar system, achieve a shape that should be reserved for objects twice its size? The answer proposed by Vanazza's team is the one we touched on earlier: catastrophic disruption and reaccumulation. The original Hygiea was struck so hard that it was completely shattered. The fragments formed a cloud of debris, a swarm of rubble expanding outward from the point of impact. Most of the mass stayed gravitationally bound. The fragments did not reach escape velocity. Over time, over perhaps hours or days, the debris fell back together. And here is the critical insight. When a cloud of rubble collapses under its own gravity, it does not form a jagged pile. If the cloud has enough angular momentum and enough total mass, and if the individual fragments are small enough to behave almost like a fluid, the collapsing debris naturally settles into a spherical shape. It is not the original rock being deformed by gravity. It is a new object being born from rubble, and the birth process itself produces a sphere. Computer simulations run by the team supported this scenario, using a method called smooth particle hydrodynamics, a computational technique that models the behavior of materials under extreme conditions by treating them as collections of interacting particles. The team simulated head-on collisions between a Hygiea-sized target and impactors of various sizes. They found that an impactor, roughly 100 kilometers in diameter, striking at a velocity of about 5 kilometers per second, could completely shatter the target body. Within hours, the debris began to gravitationally reassemble, and within a few days the largest remnant, the new Hygiea, had settled into a shape that was, remarkably, almost perfectly spherical. The simulations also explain the absence of a giant crater. If the collision completely destroyed the original body, there is no surface left to bear the scar. The crater does not exist because the object it would have been carved into no longer exists. The Hygiea we see today is not the same body that was hit. It is a new body, assembled from the ruins of the old one. The small craters, visible on its surface, are from later impacts, relatively minor events that occurred after the reassembly. Billions of years of slow, steady bombardment in the asteroid belt. But here is what makes this truly terrifying, or at least deeply unsettling for the tidy categories of planetary science. If Hygiea achieved its spherical shape through disruption and reaccumulation, then the threshold for hydrostatic equilibrium is not what we thought. The conventional wisdom said an object needed to be 900 to 1,000 kilometers across for gravity to pull it into a sphere through slow, steady internal deformation. But Hygiea did not reach equilibrium that way. It reached it through violence, through destruction and rebirth. And that means the question of how big does an object have to become round does not have a single answer. It depends on the path the object took to get there. It depends on its history. This is a problem, because the IAU definition of a dwarf planet does not specify how an object achieved hydrostatic equilibrium. It just says the object must have sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, nearly round, shape. It does not say the object must have deformed under its own gravity in the traditional sense. It does not exclude objects that became round through reaccumulation. It just says round, orbits the Sun, has not cleared its orbit. If Hygiea meets those criteria, and the sphere observations strongly suggest it does, then Hygiea is a dwarf planet. The implications ripple outward like waves from a stone dropped into still water. If an object as small as 434 kilometers can become round through catastrophic disruption and reaccumulation, then the size threshold for dwarf planet status drops dramatically. And if the threshold drops, the number of potential dwarf planets in the solar system does not just increase slightly. It could increase enormously. There are hundreds of objects in the asteroid belt and the Kuiper belt that are between 300 and 600 kilometers in diameter. Many of them have experienced catastrophic collisions. Many of them belong to asteroid families that suggest violent histories. How many of them are round? We do not know. We have never looked closely enough. And this is not just a question of taxonomy. It is not just about labels. The distinction between a rock and a world matters because it determines how we think about these objects, how we allocate resources to study them, and how we understand the history of the solar system. A round object tells a different story than an irregular one. A round object implies a level of physical complexity, gravitational processing, internal adjustment, possible differentiation that a rock does not. A round object is not just a relic. It is a world. Small, frozen, dark, yes, but a world. Something is wrong with our assumptions. The neat dividing lines that astronomers drew in 2006, planet, dwarf planet, small solar system body, were supposed to bring order to a chaotic taxonomy. Instead, Hygiea has revealed that those lines are blurrier than anyone imagined. The universe, it turns out, does not care about our categories. There is another layer to this problem, and it involves a concept that sounds straightforward, but is, in practice, fiendishly difficult to pin down. What does round actually mean? The IAU definition says a dwarf planet must have a nearly round shape. But how round is round enough? Ceres, the prototype dwarf planet in the asteroid belt, is not perfectly spherical. It is slightly oblate. wider at the equator than at the poles because of its rotation. Its equatorial diameter is about 964 kilometers, and its polar diameter is about 892 kilometers, giving it an oblateness of about 7.5%. Is that nearly round? The IAU says yes. But what about an object with 10% oblateness? 15%? 20%? Vesta has an oblateness of roughly 15%, largely due to the massive Rhea-Silvia impact basin at its south pole. The IAU does not consider Vesta to be in hydrostatic equilibrium. But where is the line? No one has formally defined it. The criterion is, in the words of several planetary scientists, frustratingly vague. Hygiea, according to the sphere measurements, has an oblateness of roughly 2 to 3%. By this measure, it is more spherical than Ceres, more spherical than the IAU's existing dwarf planet in the asteroid belt. If roundness is the criterion, Hygiea passes with room to spare, but some scientists push back. They argue that the spare images, while remarkable, have limited resolution. Each pixel in those images covers roughly 25 kilometers on Hygiea's surface. Small-scale irregularities, craters, ridges, depressions, would be invisible. The object might look round at this resolution, but be significantly less round at higher resolution. To truly confirm hydrostatic equilibrium, they argue, we would need a spacecraft flyby. We would need close-up images. We would need gravity measurements, which can reveal the internal mass distribution and determine whether the shape is genuinely in equilibrium or is just coincidentally spherical. This is a reasonable objection, and it highlights a deeper frustration in planetary science. Most of the objects in the solar system have never been visited by a spacecraft. We have sent probes to a tiny handful of worlds, a few planets, a few moons, a few asteroids, a few comets. The vast majority of objects we know about, including Hygiea, have only been studied from Earth or from Earth orbit. Our knowledge is limited by distance, by resolution, by the physics of light traveling across millions or billions of kilometers. We are making judgments about the nature of worlds based on a few smudged pixels, and yet those pixels are telling us something we cannot ignore. Consider the alternative. If Hygiea is not in hydrostatic equilibrium, if its round shape is just a coincidence, or an artifact of reassembly that does not reflect genuine gravitational equilibrium, then what does that mean? It means that the process of catastrophic disruption and reaccumulation can produce spherical shapes without hydrostatic equilibrium. It means that roundness alone is not sufficient evidence for the state that defines a dwarf planet. And it means that the IAU's criterion, which relies on shape as a proxy for internal physical state, is fundamentally flawed. Either way, the conclusion is uncomfortable. Either Hygiea is a dwarf planet, and the threshold is far lower than we thought, or Hygiea is not a dwarf planet and our primary method of identifying dwarf planets is unreliable. There is no version of this story that leaves our current framework intact. The scientists studying Hygiea are well aware of this dilemma. In their 2019 paper, Vanaza and his colleagues were careful to frame their results cautiously. They noted that Hygiea satisfies all four criteria for dwarf planet status, as currently defined by the IAU. It orbits the Sun. It is not a satellite of another planet. It has not cleared its orbital neighborhood, and its shape is consistent with hydrostatic equilibrium. But they stopped short of formally requesting reclassification. They acknowledged the limitations of their data. They called for further observations and, ideally, a dedicated spacecraft mission. That restraint speaks to the culture of planetary science. The Pluto controversy of 2006 left scars. Scientists saw a taxonomic decision become a cultural flashpoint, a dinner table debate, a punchline. The community is wary of another such episode. Reclassifying Hygiea would reopen the wound. It would force a conversation about definitions that many astronomers would prefer to avoid. But avoiding the conversation does not make the problem go away. Hygiea is round. The data says it is round, and the universe does not wait for committees to make up their minds. The deeper issue, the one that keeps planetary scientists up at night, is that Hygiea is probably not unique. The process that made it round, catastrophic disruption and reaccumulation, is not rare. It is, in fact, one of the most common processes in the asteroid belt. There are more than 100 identified asteroid families, each one the product of a catastrophic collision. Many of the parent bodies of those families were large enough that their reassembled remnants could plausibly be spherical, but we have never looked at most of them with the resolution needed to determine their shapes. Consider this possibility. There could be a dozen objects in the asteroid belt alone that are spherical enough to qualify as dwarf planets under the current definition. There could be dozens more in the Kuiper belt, where icy compositions make it even easier for objects to achieve equilibrium at smaller sizes. The solar system might not have 5 dwarf planets. It might have 50 or 500, and if it does, the category that was supposed to contain the unruly outcasts of planetary classification, the objects too big to be asteroids but too small or too poorly situated to be planets, would swell into something unwieldy. 5 dwarf planets is a manageable list, 500 is a population, and a population of dwarf planets, each with its own history, its own composition, its own formation story, changes the way we think about the solar system. It changes the relative importance of planets versus everything else. It suggests that the solar system is not a place with 8 major players and a supporting cast. It is a place with thousands of worlds, most of them small, most of them cold, most of them unknown, and each one a legitimate member of the family. This is the tension at the heart of the Hygiea story. It is not just about one asteroid, it is about the definition of worldhood. It is about where we draw the line between significance and insignificance, between something worth studying and something we can ignore. And it is about the uncomfortable possibility that we have been drawing that line in the wrong place all along. But to understand what Hygiea truly means for the future of planetary science, we need to look at the attempts, past and present, to answer these questions, the missions that have been proposed, the theories that have been tested, the tools that have been built to peer into the darkness and count the worlds. And what those efforts have revealed is, in many ways, more unsettling than the questions themselves. There is a deeper dimension to the Hygiea puzzle that connects it to one of the oldest questions in planetary science. How did the solar system get its architecture? The arrangement of the planets we see today, 4 small rocky worlds close to the Sun, then a belt of rubble, then 4 massive gas and ice giants, was once assumed to be more or less primordial. The planets formed where they are now, astronomers believed, and they have stayed there for 4.5 billion years. This tidy picture began to crumble in the 1990s and was demolished completely in the 2000s by a series of dynamical models collectively known as the NICE model, named after the city in France where it was first developed. The NICE model proposes that the giant planets did not form in their current orbits. Instead, they migrated. Jupiter and Saturn, in particular, underwent a dramatic period of orbital adjustment, roughly 500 to 700 million years after the formation of the solar system. During this upheaval, Jupiter moved slightly inward, while Saturn, Uranus, and Neptune moved outward. Neptune may have migrated outward by billions of kilometers, ploughing through a primordial disk of icy planetesimals and scattering them in every direction. Some were flung into the inner solar system. Some were ejected from the solar system entirely. Some were captured into resonant orbits with Neptune and became the Kuiper belt objects we observe today. And the asteroid belt? The belt was devastated. Jupiter's migration, even a relatively modest shift in its orbit, would have destabilized the entire belt region, perturbing asteroid orbits, increasing collision velocities, and ejecting vast quantities of material. Some models suggest that the belt lost 99% or more of its original mass during this period. The belt we see today is not the belt that existed when the solar system was young. It is a remnant, a shadow, a ghostly trace of what was once a far more massive population of objects. This history matters for Hygiea because it determines the conditions under which the Hygiea family-forming collision occurred. If the collision happened early, in the first billion years of solar system history, then it occurred in a very different environment. The belt was more crowded. Collision velocities were higher. The probability of a catastrophic disruption was greater. And the gravitational environment was more complex, with Jupiter's migration stirring the belt like a spoon in a pot. If the collision happened later, 2 or 3 billion years ago, or even more recently, then it occurred in a quieter belt, more like the one we see today. The timing matters because it affects the dynamics of the reaccumulation process. In a crowded belt, fragments from a catastrophic disruption are more likely to be perturbed by nearby objects, potentially preventing clean reassembly. In a quieter belt, the fragments have more time and more space to fall back together undisturbed. Current estimates of the Hygiea family's age, based on the dynamical dispersion of the family members' orbits, suggest a formation time of roughly 2 billion years ago. This is relatively late in solar system history, well after the late heavy bombardment, well after the major planetary migrations, in a belt that was already depleted and comparatively calm. Under these conditions, the catastrophic disruption and reaccumulation scenario becomes more plausible. The fragments would have had a relatively peaceful environment in which to reassemble. The sphere that formed from the rubble had time to settle. 2 billion years. Hygiea has existed in its current form for roughly 2 billion years. For context, 2 billion years ago on Earth, the most complex life form was a single cell. Multicellular organisms had not yet evolved. Oxygen was still a relatively recent addition to the atmosphere. The continents looked nothing like they do today. And out in the cold depths of the asteroid belt, a cloud of shattered rock was slowly, silently pulling itself into a sphere. That sphere has been orbiting the Sun ever since. Unvisited, unstudied except from the vast distance of Earth. A world, or a rock pretending to be one, waiting in the dark for someone to come and find out which. The classification question is not merely academic. It reflects a genuine philosophical and scientific tension about how we organize our understanding of the cosmos. When the IAU defined what a planet is, they were attempting to impose order on a system that resists neat boundaries. Nature does not produce categories. Nature produces a continuum. From specks of dust to gas giants, there is an unbroken spectrum of sizes, shapes, compositions, and histories. The lines we draw, planet, dwarf planet, asteroid, comet, are human inventions. They are useful, even necessary, for communication and for allocating research priorities. But they are not natural, they are imposed. And Hygiea sits right on one of those imposed lines, asking, quietly, patiently, in the language of gravity and geometry, whether the line should be moved. The question is not whether Hygiea deserves the label. The question is whether the label deserves the question. And to answer that, we need to look at how scientists have tried, and are still trying, to draw the boundaries of worldhood, to count the worlds in our solar system, and to reckon with the possibility that we have been undercounting them by orders of magnitude. There is also the matter of what Hygiea can tell us about the composition of the early solar system, which makes the stakes even higher. C-type asteroids like Hygiea are among the most scientifically valuable objects in the belt. Their dark, carbon-rich surfaces are believed to preserve material that has remained largely unchanged since the solar nebula condensed 4.5 billion years ago. They are, in a very real sense, time capsules. The meteorites associated with C-type asteroids, carbonaceous chondrites, contain amino acids, presolar grains, and tiny droplets of water locked in hydrated minerals. Some scientists believe that C-type asteroids, or objects very much like them, delivered much of the water in Earth's oceans and possibly even the organic building blocks of life. If Hygiea is a world, a body massive enough and geologically complex enough to have undergone gravitational processing, internal heating, and aqueous alteration, then its material is not merely preserved, it has been transformed. The difference matters. Pristine, unaltered chondritic material tells us about the raw ingredients of the solar system. Altered material that has been heated, compressed, mixed with water, chemically processed, tells us about the recipes, about the reactions, about the pathways by which raw cosmic dust became the stuff of planets and ultimately the stuff of life. We do not know where Hygiea falls on this spectrum. We have spectroscopic data that suggests its surface is consistent with heated and aqueously altered carbonaceous material. But spectroscopy from Earth is limited. It can tell us about the top fraction of a millimeter of the surface. It cannot tell us about the interior. It cannot tell us whether Hygiea was once warm enough for liquid water to exist in its pores. It cannot tell us whether the original Hygiea, the body that existed before the catastrophic impact, had differentiated into a core and mantle the way Vesta did, or whether it remained a homogeneous mixture throughout its history. These are not idle questions. They connect directly to one of the biggest open problems in planetary science: the delivery of water and organics to the inner solar system. Multiple lines of evidence suggest that Earth's water did not come from the local material that formed the terrestrial planets. The inner solar nebula was too hot for water ice to condense. Water had to be delivered from farther out, from the asteroid belt or beyond, by impacts during the early history of the solar system. The objects that delivered that water were almost certainly C-type or similar volatile-rich bodies. Understanding how those bodies formed, how they evolved, how they were disrupted and reassembled and scattered. Understanding, in other words, the history of objects like Hygiea is essential to understanding why Earth has oceans at all. And here is the cosmic irony. The same collision that shattered Hygiea and scattered nearly 7,000 fragments across the belt may have also sent some of those fragments on trajectories that crossed the orbits of the inner planets. Some of those fragments may have struck Earth. Some of the water in your glass, some of the carbon in your cells, may have once been part of the original Hygiea, ejected by the same impact that ultimately reshaped the remnant into the sphere we observe today. This is not science fiction. This is the logical consequence of orbital dynamics and the age of the solar system. Over billions of years, material migrates, orbits evolve, fragments wander, and some of them find their way to Earth. So the question of whether Hygiea is a dwarf planet is not just a matter of taxonomy. It is a matter of origins, our origins, and the stakes of getting it right, of understanding what this dark, round, ancient object truly is, are far higher than a simple reclassification vote. There is one more thread that needs to be woven into this story before we move forward. It concerns the observational legacy, the long chain of measurements from De Gasparis in 1849 to Vanazza in 2019 that slowly, painstakingly built up our picture of Hygiea. And it is a story of frustration as much as discovery. For most of its observational history, Hygiea was studied primarily through photometry, measuring how its brightness changes over time as it rotates. These light curves, as they are called, can reveal the rotation period of an asteroid and provide clues about its shape. If an asteroid is elongated, its brightness will vary significantly as it rotates because the cross-sectional area facing the observer changes. If it is more spherical, the light curve will be relatively flat. Hygeia's light curves were, in fact, remarkably flat. The brightness variations were small, just a few percent, suggesting a nearly symmetric shape. But astronomers were cautious. A flat light curve is consistent with a sphere, but it is also consistent with a pole-on viewing geometry, where the observer happens to be looking down the rotation axis of an elongated object. From that angle, even an irregular body can appear to have a flat light curve. Thermal infrared observations provided better size estimates. By measuring the heat radiated by Hygiea, astronomers could calculate its diameter independent of assumptions about its reflectivity. These measurements, conducted with ground-based telescopes, and later with the IRAS and Akari infrared survey satellites, converged on a diameter of roughly 430 to 440 kilometers. They also confirmed the low albedo. Hygeia's surface absorbs most of the sunlight that hits it, re-emitting the energy as infrared radiation. Stellar occultation observations, events in which Hygiea passes in front of a distant star, briefly blocking its light, provided additional shape constraints. By timing the duration of the occultation from multiple locations on Earth, astronomers could measure cross-sections of Hygeia's shadow and reconstruct its projected shape. Several occultation events observed between the 1990s and 2010s suggested a shape that was roughly circular in projection, consistent with a spherical or near-spherical body, but occultations are rare and depend on the alignment of the asteroid, the star, and the observer. Coverage was sparse. All of these lines of evidence pointed in the same direction. Hygiea was probably round, but probably is not proof, consistent with is not confirmation. And in science, the difference between probable and confirmed is the difference between a hypothesis and a discovery. It took SPARE, with its ability to directly resolve the disk of Hygiea, to actually see its shape, rather than inferring it from shadows and brightness curves to cross that threshold. The 2019 paper in Nature Astronomy was not just a shape measurement, it was the culmination of 170 years of indirect observations, each one bringing us incrementally closer to understanding a world that had been hiding in plain sight. And the picture it revealed was not the picture anyone expected. The story of how we have tried to understand the small, dark worlds of the solar system is, in many ways, a story of humility. It is a story of machines built to answer simple questions that came back with complicated answers. It is a story of theories proposed with confidence and discarded with reluctance. And it is a story in which Hygiea, this quiet, overlooked sphere, appears again and again at the margins, waiting for its turn in the spotlight. The first attempt to understand objects like Hygiea came not from space, but from the ground. And it began with light. In the 1970s and 1980s, a revolution was underway in asteroid science. Astronomers had developed a technique called spectrophotometry, measuring the intensity of light reflected by an asteroid at many different wavelengths that could reveal the mineral composition of an asteroid's surface. Different minerals absorb and reflect light at different wavelengths, creating characteristic spectral fingerprints. Iron-rich silicates produce absorption features at certain infrared wavelengths. Water-bearing clays produce features at others. Carbon-rich materials tend to flatten and darken the entire spectrum. Using this technique, astronomers began to classify asteroids into taxonomic types. S-types, rich in silicates, dominated the inner belt. C-types, rich in carbonaceous material, dominated the outer belt. M-types, with metallic spectral signatures, were scattered throughout. The taxonomy grew more complex over time. V-types for Vesta-like basaltic compositions, D-types for the dark, reddish objects in the outer belt and among the Jupiter Trojans. But the broad pattern held. The inner belt was rocky, the outer belt was carbon-rich, and the boundary between them roughly corresponded to the snow line, the distance from the Sun, beyond which water ice could survive in the early solar nebula. Hygiea fell squarely in the C-type category. Its spectrum was dark, flat and featureless, consistent with carbonaceous chondrite material. This was useful but not surprising. What was surprising was how little its spectrum told us. C-type spectra are notoriously bland. Unlike S-types, which display sharp absorption features that allow detailed mineralogical analysis, C-type spectra are nearly featureless across most of the visible and near-infrared range. There are faint absorption bands near 0.7 micrometers associated with iron-bearing phyllosilicates, and sometimes a subtle feature near 3 micrometers associated with water or hydroxyl groups. But these features are weak, and for an object as dark as Hygiea, reflecting only 6% of incoming light, they are difficult to measure with precision. The result was that for decades, Hygiea's composition remained poorly constrained. We knew it was dark, we knew it was probably carbonaceous, we knew it was probably primitive. But the details, the specific mineralogy, the degree of aqueous alteration, the fraction of organics versus silicates versus ices, remained tantalizingly out of reach. The first major space-based attempt to study asteroid belt objects came in 1991, when NASA's Galileo spacecraft, en route to Jupiter, flew past the asteroid Gaspra. It was the first close-up look at a main-belt asteroid, and the images were revelatory. Gaspra was small, roughly 18 kilometers long, and irregularly shaped, like a distorted potato covered in craters and grooves. 2 years later, Galileo flew past a second asteroid, Ida, and discovered that Ida had a tiny moon, the first confirmed asteroid satellite, named Dactyl. These flybys demonstrated that asteroids were far more complex and varied than anyone had assumed from Earth-based observations. But neither Gaspra nor Ida was a large, dark outer belt C-type like Hygiea. They were S-type objects from the inner belt, geologically interesting, but compositionally different. The large C-types remained unvisited. The first dedicated asteroid mission came in 2003, when NASA launched the Dawn spacecraft. Dawn was designed to visit the two largest objects in the asteroid belt, Vesta and Ceres. It would orbit each one, mapping their surfaces, measuring their compositions, and determining their internal structures. It was, in the words of its principal investigator Chris Russell, a mission to the beginning of the solar system. Dawn arrived at Vesta in July of 2011. What it found was extraordinary. Vesta was not just a large asteroid. It was a differentiated protoplanet, a body that had once been hot enough for its interior to separate into a dense metallic core, a silicate mantle, and a basaltic crust. It had experienced volcanic activity. Its surface was covered in a stunning variety of geological features. Craters, ridges, troughs, landslides, dark material deposits of unknown origin, and the enormous Reasselvia impact basin at the South Pole. A crater so large that its central peak towered 22 kilometers above the basin floor. The Reasselvia basin was key. Its scale, nearly 500 kilometers in diameter on a body only 525 kilometers across, showed that Vesta had survived a collision catastrophic enough to have completely destroyed most objects of similar size. Numerical simulations suggested the impactor was roughly 66 kilometers in diameter and struck at about 5.4 kilometers per second. The collision excavated roughly 1% of Vesta's volume, sent fragments all the way to Earth as a specific class of meteorites known as howardites, eucrites, and diogenites, and created a family of small Vestoid asteroids that still orbit near Vesta today. But Vesta was not round. Despite being larger than Hygiea, despite having a differentiated interior, despite having survived billions of years, Vesta's shape remained distinctly irregular, flattened at the South Pole by the Reasselvia impact, oblate from its rotation, lumpy and asymmetric. The Dawn gravity measurements confirmed that Vesta is not in hydrostatic equilibrium. Its shape is dominated by the rigidity of its rock and by the scars of ancient impacts, not by the smooth pull of gravity. This made Hygiea's roundness even more puzzling. Vesta is bigger. Vesta is denser. Vesta has a more differentiated interior. And Vesta is not round. Hygiea is smaller, less dense, less differentiated. And yet, according to the sphere data, it is more spherical. The conventional logic, bigger means rounder, was turned upside down. The Dawn team discussed this paradox. How could a smaller, less massive object achieve a shape that a larger, more massive one could not? The answer kept coming back to the same hypothesis. History matters more than size. Vesta's shape is irregular because Vesta was never fully disrupted. It survived its catastrophic impact. The Reasselvia basin is a scar, but Vesta itself was never shattered. Its shape preserves the memory of that impact, frozen into the rock. Hygiea, by contrast, was completely destroyed and reassembled. Its shape does not preserve the memory of anything, because the body that carried those memories no longer exists. The sphere we see is new, fresh, born from a cloud of rubble that had no memory at all, and a memoryless body, collapsing under its own gravity, has only one shape available to it. In September of 2015, Dawn left Vesta and entered orbit around Ceres, the largest object in the asteroid belt. Ceres was a different world entirely. Where Vesta was rocky, cratered and harsh, Ceres was smooth, muted and icy. Its surface was covered in a dark material consistent with a mixture of clays, carbonates and salts. There were bright spots, famously bright, dazzlingly bright, in a crater called Ocheta, which Dawn revealed to be deposits of sodium carbonate, a type of salt. The best explanation was that briny water had somehow made its way from Ceres's interior to its surface, erupting through cracks in the crust and leaving salt deposits behind as it sublimated in the vacuum of space. Ceres, it turned out, was not just an asteroid. It was a geologically active world with an icy interior and a subsurface ocean, or at least a briny layer, of liquid water. The round shape of Ceres was consistent with hydrostatic equilibrium. Its internal heat and the weakness of its icy composition allowed gravity to mold it into a near-perfect sphere over billions of years. This was the standard model of how small bodies become round. They form gradually, they heat up, their interiors weaken, and gravity pulls them smooth. Hygiea did not follow this path. It followed the other path, the violent one, and the Dawn mission, for all its brilliance, could not tell us anything about Hygiea directly. Hygiea was not on Dawn's itinerary. It was not even considered for an extended mission. The spacecraft's ion thrusters eventually ran out of xenon propellant, and Dawn became an inert satellite of Ceres, orbiting silently in the darkness of the belt. It remains there today, a monument to what we learned, and a reminder of how much we left undone. The next chapter in the story belongs not to a spacecraft, but to a telescope. And not just any telescope, the James Webb Space Telescope, launched on the 25th of December 2021 and positioned at the Sun-Earth Lagrange point 2, 1.5 million kilometers from Earth on the side opposite the Sun. JWST was designed primarily for cosmology, for studying the first galaxies, the earliest stars, the faint glow of the cosmic microwave background. But its infrared sensitivity also makes it an extraordinarily powerful tool for studying solar system objects. Its instruments can detect and measure absorption features in asteroid spectra with a precision that ground-based telescopes cannot match, because JWST operates above Earth's atmosphere, which absorbs much of the infrared light that astronomers need to study. Several teams have proposed JWST observations of Hygiea and other large C-type asteroids. The goals are straightforward but scientifically crucial. Measure the 3 micrometer water feature in Hygiea's spectrum with high precision. Search for signatures of specific hydrated minerals and organic compounds, and compare Hygiea's surface composition with the compositions of known carbonaceous chondrite meteorites, and with the samples returned from asteroids Ryugu and Bennu. The numbers are striking. JWST's mid-infrared instrument, known as MIRI, operates at wavelengths between 5 and 28 micrometers, a range that covers the thermal emission peak of objects at Hygea's distance from the Sun. This means MIRI can simultaneously measure the reflected light and the thermal emission of Hygeia, providing constraints on both composition and physical properties. Combined with JWST's near-infrared spectrograph, known as NIRSpec, which covers wavelengths from 0.6 to 5.3 micrometers, a comprehensive spectral portrait of Hygeia is possible, far more detailed than anything achieved from the ground. But even JWST has limitations. It can tell us what is on the surface. It cannot tell us what is inside. For that, we need gravity measurements, which require a spacecraft in orbit, and no spacecraft mission to Hygeia has been approved. This is not for lack of ideas. Several mission concepts have been proposed over the years, usually as part of larger surveys of the asteroid belt or as dedicated flyby missions. In the European Space Agency's Cosmic Vision program, a concept called Asteroid was proposed in the early 2010s to visit multiple asteroids, including at least one large C-type. The concept was not selected. In the United States, a mission concept called Psyche, designed to visit the metallic asteroid of the same name, was selected in 2017 and launched in 2023. Psyche will orbit a metal-rich M-type asteroid, not a carbonaceous C-type. It will provide groundbreaking data about metallic cores and planetary differentiation. But it will tell us nothing about Hygeia. The closest any approved mission comes to addressing the Hygeia question is the Lucy mission, launched by NASA in October of 2021. Lucy is designed to visit the Jupiter Trojan asteroids, dark, primitive objects that share Jupiter's orbit, leading and trailing the giant planet by 60 degrees. The Trojans are believed to be compositionally similar to C-type asteroids and may have originated in the same region of the early solar system. By studying the Trojans, Lucy may provide indirect constraints on the nature of objects like Hygeia, but Lucy will not visit the main belt. It will fly past its Trojan targets at high speed, collecting data in brief encounter windows. It is a survey mission, not an orbital mission, and it is not going to Hygeia. The result is that Hygeia remains, as of now, one of the largest unvisited objects in the inner solar system. We have sent spacecraft to asteroids smaller than a kilometer. We have orbited Vesta and Ceres. We have collected samples from Ryugu and Bennu and brought them home to Earth. But the fourth largest asteroid in the belt, the one that might be a dwarf planet, the one that was destroyed and reborn, the one whose shape challenges our definitions and whose composition may hold clues to the origin of Earth's water, has never been visited, has never been seen up close, has never been touched. This gap in our exploration is not an accident. It reflects priorities. Space missions are expensive, typically hundreds of millions to several $billion, and the agencies that fund them must choose carefully. The scientific community uses peer review panels, decadal surveys, and competitive proposal processes to decide which missions fly. In those competitions, targets with compelling scientific cases and clear, answerable questions tend to win. And for a long time, Hygeia's scientific case was too uncertain. Its shape was unknown. Its composition was poorly constrained. The questions it raised were important, but diffuse. Why send a billion-dollar spacecraft to an object when we are not even sure what the right questions are? The 2019 SPARE results changed that calculus. The discovery that Hygiea is spherical gave it a scientific case that it did not have before. A dwarf planet candidate in the asteroid belt, smaller than any known dwarf planet, formed through a process that challenges our models. That is a compelling target. Since the publication of the Vanadza paper, several groups have begun developing mission concepts specifically for Hygiea. Some propose a flyby, some propose an orbiter, some propose a combination, with a primary spacecraft orbiting Hygiea and one or more small CubeSats released to study the object from different vantage points. But concept studies are not missions. Proposals are not launches, and the timeline of space exploration is measured in decades, not years. Even if a Hygiea mission were selected tomorrow, it would likely not launch until the early 2030s at the earliest, and would not arrive at Hygiea until the late 2030s or early 2040s, depending on the trajectory. The answers are not coming soon. In the meantime, astronomers are doing what they have always done. They are using the tools they have: ground-based telescopes, space telescopes, computer simulations, meteorite analyses, to squeeze every drop of information out of the photons that arrive from Hygiea's direction. And one of the most promising avenues of investigation involves not Hygiea itself, but its family. The Hygiea family, those nearly 7,000 fragments scattered across the outer main belt, is a treasure trove of information. Each fragment is, in a sense, a piece of the original Hygiea, ejected by the catastrophic collision and preserved in its own orbit for roughly 2 billion years. By studying the compositions, sizes, shapes, and orbits of the family members, astronomers can reconstruct the conditions of the original impact and the properties of the body that was destroyed. Recent work using data from the Sloan Digital Sky Survey and from the European Space Agency's Gaia mission has refined the membership list of the Hygiea family and revealed some unexpected features. The size distribution of the family members, the relative numbers of large versus small fragments, follows a pattern that is consistent with a catastrophic disruption followed by gravitational reaccumulation. There is a clear gap in the size distribution between Hygiea itself at 434 kilometers and the next largest member, which is only about 35 to 40 kilometers across. This gap is characteristic of a super-catastrophic event, a collision so violent that the fragments were thoroughly comminuted, ground down to small sizes, before the largest piece could reassemble. The orbital distribution of the family provides additional clues. The family members are spread over a range of semi-major axes, eccentricities, and inclinations that is consistent with a high-velocity impact, not a gentle, low-energy breakup. The spread in velocity required to produce the observed orbital dispersion is on the order of several hundred meters per second, comparable to the escape velocity from the original Hygiea body. This confirms that the impact was energetic enough to completely disrupt the target, scattering fragments at speeds near or above the speed needed to permanently escape. But here is where it gets stranger. Some recent analyses of the Hygiea family have identified what appear to be interlopers, objects whose orbits and spectral properties place them within the family's boundaries, but whose compositions do not match. These interlopers may be background asteroids that happen to have similar orbits, or they may be fragments from the impactor itself, which could have had a different composition from the target. Disentangling family members from interlopers is one of the major challenges in asteroid family studies, and it becomes more difficult for older, more dispersed families like Hygiea's. There is also the question of what happened to the material that was not reaccumulated into the current Hygiea. The family as a whole has a total mass that is significantly less than the estimated mass of the original Hygiea body. Some mass was lost to grinding. Collisions between fragments reduced them to dust-sized particles that were eventually swept away by radiation pressure and the Poynting-Robertson effect, a process by which sunlight gradually spirals small particles inward toward the sun. Some mass may have been ejected from the belt entirely, perturbed by Jupiter's gravity onto trajectories that sent it into the inner solar system or out into interplanetary space. And some of that ejected mass may have landed on Earth. This is not speculation. Meteorite delivery from the asteroid belt is a well-documented process. The dynamical pathways are understood. Resonances with Jupiter's orbital period, particularly the 3:1 mean motion resonance and the nu-6 secular resonance, can pump up the eccentricities of belt objects and send them onto Earth-crossing orbits. Once on Earth-crossing orbits, they may survive for millions of years before eventually colliding with one of the terrestrial planets, or being ejected from the inner solar system by a close encounter with Jupiter. Carbonaceous chondrite meteorites make up roughly 3 to 5% of all meteorite falls on Earth. Some of them may originate from the Hygiea family. Identifying a specific meteorite as a Hygiea fragment would be extraordinarily difficult. It would require matching the meteorite's oxygen isotope ratios, trace element abundances, and spectral properties to the properties of Hygiea and its family members. But the possibility exists. Every time you pick up a dark, crumbly meteorite from a desert floor or museum collection, you might be holding a piece of a world that was destroyed and reborn 2 billion years ago. This brings us to the most recent and, in many ways, the most exciting chapter in the Hygiea story: the sample return missions. In December of 2020, Japan's Hayabusa 2 mission returned to Earth, carrying 5.4 grams of material collected from the surface of asteroid Ryugu, a small C-type asteroid roughly 900 meters in diameter. In September of 2023, NASA's OSIRIS-REx mission returned with roughly 121 grams of material from asteroid Bennu, another small C-type of similar size. These were the first samples of carbonaceous asteroid material ever brought to Earth for laboratory analysis. The results were extraordinary. Both samples contained abundant hydrated minerals, clays and fissilicates formed by the interaction of silicate rock with liquid water at moderate temperatures, likely in the interior of a larger parent body that has since been disrupted. Both contained a rich inventory of organic molecules, including amino acids, nucleobases, and a variety of complex carbon compounds. The Ryugu sample, in particular, was found to have a composition remarkably similar to a specific type of carbonaceous chondrite called Ci chondrites, the most chemically primitive meteorites known. Their elemental abundances match the composition of the Sun more closely than any other material available for study. These discoveries have profound implications for Hygiea. Ryugu and Bennu are small fragments, rubble pile asteroids only a few hundred meters across. They are children of larger parent bodies that were destroyed in ancient collisions. If those parent bodies were anything like Hygiea, large, C-type, volatile-rich, possibly aqueously altered, then the Ryugu and Bennu samples may be telling us what Hygeia's material looks like up close. Not exactly, of course. Different parent bodies have different histories, different temperatures, different degrees of processing, but the broad picture, hydrated minerals, organics, primitive compositions, is likely applicable. And if it is, then Hygiea is sitting on a treasury of material that planetary scientists would give almost anything to study. Material that preserves the chemistry of the early solar system. Material that may contain clues to the origin of water and life on Earth. Material that has been locked away in the cold, dark outer belt for 4.5 billion years, protected by distance and darkness from the very scientists who are desperate to analyze it. The irony does not escape those scientists. We have the tools, we have the experience, we have the motivation. What we lack is the mission, and so Hygiea waits. Round, dark, cold, and patient. A world that was destroyed and remade, circling the Sun in the outer reaches of the belt, surrounded by the scattered remains of its former self. A world that may hold answers to questions we have not yet thought to ask. A world that, according to the rules we wrote ourselves, might deserve a title we have never given it. The question is whether we will ever go and find out. But there is one more avenue of exploration that deserves attention, and it involves a question that connects Hygiea to a broader revolution in our understanding of the small bodies of the solar system. What happens inside these objects? For decades, the internal structures of asteroids were essentially unknown. Astronomers could measure their sizes, shapes, rotation periods, and surface compositions, but the interiors were invisible. Were they solid rocks? Were they rubble piles? Were they differentiated, with dense cores and lighter crusts? Were they porous, riddled with voids? Or were they some combination of all of these, varying from object to object in ways that reflected their individual histories? The answer, it turned out, was all of the above, and the evidence came from an unlikely source: density. If you know the mass of an object and its volume, you can calculate its bulk density. And if that bulk density is significantly lower than the density of the material the object is made of, you can infer that the object is porous, that it contains empty space. This is exactly what scientists found when they began measuring asteroid densities in detail. Object after object came back with densities lower than their constituent minerals. Mathilde, a 46-kilometer C-type asteroid visited by the Near-Shoemaker spacecraft in 1997, had a density of only 1.3 grams per cubic centimeter, barely denser than water and far less dense than the carbonaceous chondrite material it appeared to be made of. The implication was that Mathilde was roughly 50% empty space, half void, a floating sponge of rock. Hygeia's density, at roughly 2 grams per cubic centimeter, is also lower than solid carbonaceous chondrite material, which typically has a grain density of about 2.4 to 2.8 grams per cubic centimeter. This suggests a porosity of roughly 20 to 30%. But there is a crucial question: is that porosity macroscopic? Large voids, gaps and cavities between boulders, or microporosity, tiny pores within the mineral grains themselves? The distinction matters because it affects how the material responds to gravity. Macroporosity is relatively easy to close. Gravitational compression can crush the voids and compact the rubble over geological time. Microporosity is much harder to eliminate because it requires pressures high enough to deform the mineral grains themselves. An object with high macroporosity but low microporosity could in principle compact itself into a denser, more spherical shape over billions of years. An object with high microporosity might resist compaction no matter how long it waits. Hygeia's reassembly from a catastrophic disruption adds another dimension to this question. During the reaccumulation process, the fragments that fell back together would have initially formed a loosely packed rubble pile with high macroporosity. Over the subsequent 2 billion years, gravitational compaction, minor impacts, and thermal cycling, the slow expansion and contraction caused by Hygeia's 27.5-hour day-night cycle, may have gradually reduced that porosity, tightening the rubble, closing the voids, and smoothing the shape. The rate of this compaction process depends on the mechanical properties of the material, its strength, its friction angle, its cohesion, all of which are poorly constrained for carbonaceous chondrite material under the conditions found in the outer asteroid belt. Laboratory experiments on meteorite analogues provide semblance, but extrapolating from centimeter-scale lab samples to a 400-kilometer world is fraught with uncertainty. The physics is scale-dependent. What is rigid at small scales can flow at large scales, given enough time and enough pressure. This is where the story of Hygiea intersects with one of the most active frontiers in planetary science: the study of granular mechanics in low-gravity environments. When Hayabusa 2's small carry-on impactor struck the surface of Ryugu in April of 2019, creating an artificial crater to expose fresh subsurface material, the resulting ejector pattern revealed that Ryugu's surface material behaved more like cohesionless sand than like solid rock. The grains were loose. They moved easily. They responded to impacts in ways that could be modeled using the physics of granular flow, not the physics of solid mechanics. If Hygeia's interior behaves similarly, if it is a granular medium rather than a solid body, then its ability to achieve and maintain a spherical shape becomes more understandable. A granular medium under self-gravity tends to settle into an equilibrium configuration that is, approximately, an oblate sphere, with the degree of oblateness determined by the rotation rate and the angle of repose of the material. For Hygeia's slow rotation, once every 27.5 hours, the expected oblateness is small, a few percent at most, which is, in fact, exactly what the spare observations show. This is not a proof. It is a hypothesis, one of several, and it has not been tested with the kind of data that would settle the question. But it offers a pathway by which an object as small and as cold as Hygiea could maintain a spherical shape without requiring the kind of internal heat or icy composition that is normally invoked for larger bodies. Granular mechanics, not material weakness, may be the key. And if that is the key, then the implications are enormous, because granular mechanics is universal. Every rubble pile asteroid in the solar system is a granular body. Every catastrophically disrupted and reaccumulated asteroid is a granular body. If granular mechanics can produce spherical shapes at sizes as small as 400 kilometers, then the population of potentially spherical objects in the solar system may be far larger than anyone has estimated. The math is striking. There are roughly 200 known asteroids larger than 100 kilometers in diameter. Of those, perhaps 30 to 50 are members of large asteroid families produced by catastrophic disruptions. Many of those largest remnants could have undergone the same reaccumulation process as Hygiea. We simply have not looked at them with sufficient resolution to determine their shapes. And this is just the asteroid belt. In the Kuiper belt, where water ice is abundant and material strengths are lower, the threshold for sphericity could be even smaller. Some models suggest that icy bodies as small as 200 to 300 kilometers could achieve hydrostatic equilibrium. If those models are correct, the Kuiper belt alone could contain dozens, perhaps hundreds, of spherical bodies. Dozens of dwarf planet candidates, dozens of worlds, hidden in the darkness beyond Neptune, waiting to be resolved. The solar system may be full of worlds. Not the kind we grew up learning about, the 8 grand planets with their rings and moons and atmospheres, but small worlds. Cold worlds, dark worlds. Worlds made of rubble and ice and ancient carbon. Worlds that nobody talks about because nobody has ever seen them clearly enough to know what they are. And Hygiea may be the first one to step out of the shadows. There is one more chapter in this story of exploration that deserves telling, because it illustrates both the ingenuity and the limitations of studying distant objects from Earth. It involves radar astronomy, the practice of transmitting radio waves at a solar system object and analyzing the reflected signal is one of the most powerful tools available for studying asteroids. The Arecibo Observatory in Puerto Rico, before its tragic collapse in December of 2020, was the premier facility for asteroid radar. Its 305-meter dish could transmit microwave pulses powerful enough to bounce off asteroids millions of kilometers away, and the returning echoes carried information about the target's size, shape, rotation, surface roughness, and even the presence of moons. Radar was used to study dozens of near-Earth asteroids in exquisite detail, producing three-dimensional shape models with resolutions of tens of meters, far beyond what optical telescopes could achieve. But radar has a fundamental limitation. It works best on nearby objects. The strength of the return signal decreases with the fourth power of the distance. Double the distance, and the signal drops to 1/16 of its previous strength. For main belt asteroids like Hygiea, at distances of 300 million kilometers or more, the signal is devastatingly weak. Arecibo did attempt radar observations of a few large main belt asteroids, including Ceres and Vesta. The results were useful but limited. Rough shape constraints, surface roughness estimates, not the detailed three-dimensional models that radar could produce for nearby objects. Hygiea, smaller and farther than either Ceres or Vesta, was at the edge of Arecibo's capability. Radar echoes from Hygiea have been reported in the scientific literature, but they are faint and provide only the coarsest constraints on size and surface properties. With Arecibo gone, the remaining radar facilities, the Goldstone Deep Space Communications Complex in California, and the Green Bank Telescope in West Virginia, sometimes used in a bistatic configuration with Goldstone, have less sensitivity. The loss of Arecibo was a blow to asteroid science that is still being felt. Plans for a next-generation radar facility have been proposed, but as of now, no replacement has been funded or built. This means that one of the most powerful tools for studying asteroid interiors, radar tomography, which uses the penetration of radio waves into an asteroid's surface to probe the subsurface structure, is essentially unavailable for Hygiea. We cannot peer beneath Hygeia's dark surface using radar. We cannot map its subsurface layers, detect internal voids, or determine whether it has a coherent interior or a granular one. Those answers require either a much more powerful radar facility than anything currently in existence, or a spacecraft. Thermal modeling has provided additional, though indirect, constraints. By measuring Hygeia's thermal emission across multiple wavelengths and at different points in its orbit, astronomers can estimate its thermal inertia, a measure of how quickly its surface heats up and cools down. High thermal inertia means the surface is rocky, compact, and conducts heat well. Low thermal inertia means the surface is covered in fine regolith, loose, powdery material that insulates the subsurface from temperature changes. Hygeia's thermal inertia, as estimated from Spitzer Space Telescope and WISE satellite data, appears to be relatively low, consistent with a surface covered in fine-grained regolith. This is typical of large C-type asteroids, and is consistent with the expected outcome of billions of years of micrometeorite bombardment, which grinds surface material into progressively finer particles. The regolith layer may be meters deep, covering whatever larger-scale surface features exist beneath it. But there is a subtlety here. Fine regolith can also mask the true shape of the underlying body. If Hygeia's surface is covered in a thick blanket of loose material, that blanket would tend to smooth out topographic variations, filling in craters and softening ridges. The apparent smoothness and roundness observed by SPARE could be, in part, an artifact of this blanketing effect. The underlying shape might be less perfectly spherical than the surface suggests. This is a real concern, and it has been raised by several researchers. The counter-argument is that the SPHERE measurements are consistent with the overall dimensions of the body, not just the surface smoothness. The global shape, the relationship between the major axes, is what determines whether the body is in hydrostatic equilibrium, and that global shape is robust against surface blanketing effects. Regolith can smooth out local features, but it cannot change the global dimensions of a 400-kilometer object. Still, the debate continues, and it will continue until we have data of sufficient quality to settle it. Data that at present can only come from a spacecraft. The frustration felt by planetary scientists studying Hygiea is palpable. In an era when we have landed robots on Mars, flown through the plumes of Enceladus, and returned samples from 2 different asteroids, the idea that the 4th largest object in the asteroid belt remains unvisited seems almost absurd. The technology to visit Hygiea exists. Solar electric propulsion, proven by the Dawn mission, could carry a spacecraft from Earth to Hygiea in roughly 4 to 6 years, depending on the trajectory. Miniaturized instruments, developed for CubeSat missions and small spacecraft, could provide the gravity measurements, spectroscopic analyses, and high-resolution imaging needed to settle the dwarf planet question once and for all. What is missing is not capability. It is will, it is funding, it is the collective decision made by space agencies and review panels and funding committees that Hygiea is worth the investment. And that decision, in the end, depends on how we answer the question at the heart of this story. Does Hygiea matter? If Hygiea is just another asteroid, a lump of rubble that happens to be sort of round, then perhaps it does not matter enough to justify a billion-dollar mission. But if Hygiea is a dwarf planet, a world, with all that the word implies, then it matters enormously. It matters for the science, it matters for the definitions, and it matters for our understanding of ourselves, of our origins, of the place we occupy in a solar system that is far more complex and far more populated than the textbook version suggests. The evidence says it is a world. The definitions say it is a world. The only thing stopping us from calling it a world is our own reluctance to admit that the universe has more worlds than we planned for. It is late, the sky is dark, and somewhere out there, beyond the glare of city lights and the haze of the atmosphere, beyond the moon and beyond Mars, a sphere of ancient rock orbits the sun in silence. It has been doing this for 2 billion years. It will continue doing this for billions more. It does not know it is being discussed. It does not know it is being debated. It does not know that a species of primates on the 3rd planet from the sun has spent 170 years trying to decide what it is. But it is round, and that, somehow, is enough to challenge everything. Let us step back from the data and the definitions for a moment. Let us think about what it means that this object exists at all. The universe is not obligated to produce round things. Roundness is expensive. It costs energy. It requires mass, gravity, time, and the right conditions. Most of the solid objects in the solar system are not round. They are jagged, lumpy, elongated, cratered, fractured remnants of violent histories. They are the wreckage of a construction project that was never completed. The asteroid belt alone contains millions of such objects, each one carrying the scars of billions of years of collisions, each one frozen in whatever shape chance and physics imposed upon it. Being irregular is the default, being round is the exception. And yet, here is Hygiea, a body that was shattered, literally torn apart, and somehow emerged from that annihilation in the most ordered shape that physics can produce. A sphere, the shape of stars, the shape of planets, the shape of water droplets in free fall, the shape that gravity has been making since the universe was born, whenever it is given enough material and enough time. Let that sink in. The destruction of the original Hygiea was not a gentle process. It was not a controlled demolition. It was a catastrophe on a scale that defies human imagination. An impactor the size of a small moon struck at speeds that would carry it from Cairo to London in under 90 seconds. The kinetic energy released was greater than the total energy output of the Sun over several seconds. The target body, a world in its own right, 400 kilometers of rock and ice and carbon, that had been quietly orbiting the Sun for 2.5 billion years, was obliterated, reduced to a cloud of fragments, a swarm of rubble expanding outward from the point of impact. And in that swarm something happened. Something that should not happen to objects this small, this cold, this far from any source of heat or energy. Gravity took over. The fragments slowed. They stopped expanding. They began to fall back. And as they fell, as they collided and stuck and accumulated, the cloud contracted and collapsed and settled. And the shape that emerged from the wreckage was not random. It was not chaotic. It was round. This is not science fiction. This is the observed reality of an object that exists right now, orbiting the Sun between Mars and Jupiter, visible through any sufficiently powerful telescope. The mechanics of it are well understood. Smooth particle hydrodynamics simulations reproduce the process with remarkable fidelity. But understanding the mechanics does not diminish the strangeness. It deepens it, because the question is not just how, the question is why. Why should gravity care about geometry? Why should the collapse of a cloud of rubble produce the same shape as the collapse of a cloud of gas that forms a star? Why should the mathematics of self-gravitation, operating on scales ranging from a few hundred kilometers to millions of light years, always converge on the same answer? The answer is embedded in the deepest structure of physics. A sphere minimizes the gravitational potential energy of a self-gravitating mass. It is the shape in which every point on the surface is equidistant from the center of mass. It is the shape in which no part of the surface is higher than any other part relative to the gravitational field. It is, mathematically, the solution to a minimization problem, the arrangement that costs the least energy to maintain. And nature, given enough time and enough freedom, always finds the minimum. This is why planets are round. This is why stars are round. This is why the largest moons are round and the smallest ones are not. There is a threshold, a critical size at which the gravitational forces pulling inward overcome the material strength pushing outward, and above that threshold, everything becomes a sphere. Below it, objects can be any shape at all. They are free, they are unconstrained, they are irregular because they can be. Above the threshold, there is only one shape allowed. The universe permits no creativity above that line, only spheres, and Hygiea, impossibly, appears to be above that line, not because it was born there, not because it grew slowly and steadily until gravity overcame its rocky skeleton, but because it was blasted apart and reassembled in a process that, temporarily, made its material behave not like rock but like a fluid. The fragments during the reaccumulation were small enough and numerous enough and energetic enough to flow, and flowing material in a gravitational field makes a sphere. The implications reach far beyond the asteroid belt. Consider what this tells us about the processes that built the planets themselves. The earliest stages of planet formation, the aggregation of dust into pebbles, pebbles into boulders, boulders into planetesimals, planetesimals into protoplanets, were dominated by collisions. Some of those collisions were gentle, leading to growth. Some were violent, leading to disruption. And some were in between, catastrophic enough to shatter a body, but not energetic enough to completely disperse the fragments. Those intermediate collisions, the ones that disrupt and reaccumulate, may have been a common pathway for the formation of spherical bodies in the early solar system. If that is true, then many of the round objects we see today, not just Hygiea, but potentially some of the large moons, some of the Kuiper Belt objects, even some of the dwarf planets, may owe their shapes not to slow, gentle gravitational relaxation, but to violent disruption and rebirth. The solar system's population of round worlds may be, to a greater extent than previously appreciated, a population of phoenixes, objects that were destroyed and remade, worlds born from violence. This perspective changes the way we think about what a world is. In the traditional view, a world is something that formed. It grew. It accumulated material, heated up, differentiated, developed a surface, and maybe an atmosphere. Its roundness is a sign of maturity, a mark of having grown large enough for gravity to take over. In this new view, a world can also be something that was made, not by a creator, but by a catastrophe. A world can be the product of destruction rather than construction. And its roundness is not a sign of maturity. It is a sign of resurrection. Let that sink in. There is a philosophical dimension to this that is difficult to ignore. Humans have always drawn lines between the living and the dead, the significant and the insignificant, the worthy of attention and the easily dismissed. We do the same thing with celestial objects. Planets are important, asteroids are not, worlds matter, rocks do not. These categories reflect our values as much as they reflect physical reality. And Hygiea, sitting precisely on the boundary between rock and world, forces us to examine those values. What makes something a world? Is it size? Hygiea is smaller than many moons that we do not call worlds. Is it shape? Hygiea is rounder than some moons that we do call worlds. Is it complexity? We do not know how complex Hygiea is because we have never looked closely. Is it potential? Hygiea may contain water ice, organic molecules, and the building blocks of life. Is that not potential enough? Or is a world simply whatever we decide it is? A human category, imposed on a universe that does not share our need for labels. The astronomer and writer Phil Plait once noted that the debate over Pluto's planetary status generated more public passion than almost any other topic in modern astronomy. People cared about Pluto not because of its physical properties. Most people could not have told you its diameter or composition, but because of what it represented. Pluto was the underdog, the runt of the planetary litter, the smallest, the farthest, the most eccentric, and stripping it of its title felt to many like an act of cosmic injustice. Hygiea does not have Pluto's emotional baggage. It does not have a cultural legacy. It has not been the 9th planet for 76 years. It has no fan base, no hashtags, no bumper stickers. But the question it raises is the same question Pluto raised, sharpened to a finer point. If an object is round, orbits the Sun, and has not cleared its orbit, if it meets every criterion in the definition, does the definition apply? Or does the definition only apply to the objects we already decided were special? This question echoes in the broader history of science. Classification systems are powerful tools. They allow us to organize knowledge, communicate efficiently, and identify patterns. But they are also traps. They tempt us to mistake the map for the territory, to assume that because we have named something, we understand it. The history of biology is full of examples. Species that were classified as separate but turned out to be the same, or classified as the same but turned out to be different. The categories served us until they didn't, and when they failed, we had to choose between defending the categories and following the evidence. Hygiea is the evidence. The question is whether we are willing to follow it. There is another dimension to the deeper truth of Hygiea, and it involves time. The temporal scale of this story is almost impossible for a human mind to hold. Consider, the collision that destroyed the original Hygiea and created the Hygiea family occurred roughly 2 billion years ago. 2 billion years. When that collision happened, Earth was a very different place. The atmosphere contained no significant free oxygen. The oceans were a murky green, rich in dissolved iron, that gave them a color nothing like the blue we know today. The most complex organisms on the planet were single-celled, bacteria and archaea, living in mats and biofilms, eking out existence through metabolisms that modern biologists can barely replicate in the laboratory. Multicellular life did not exist. Animals did not exist. Plants did not exist. The continents were arranged in a configuration called Columbia, a supercontinent that bore no resemblance to any modern geography. And out in the asteroid belt, a world was dying and being reborn. Since that moment, everything has changed on Earth. Oxygen accumulated in the atmosphere. Complex cells, eukaryotes, evolved. Multicellular life appeared. The Cambrian explosion produced an astonishing diversity of animal forms. Fish colonized the oceans. Plants colonized the land. Dinosaurs rose and fell. Mammals diversified. Primates evolved. Humans appeared, developed language, built cities, invented telescopes, and pointed them at the sky. And throughout all of that, every heartbeat, every extinction, every civilization that rose and crumbled, Hygiea was there, orbiting, silent, round, unchanged. The same sphere of reassembled rubble, making the same circuit around the sun every 5.6 years, reflecting the same dim percentage of sunlight, holding the same secrets in its frozen interior. We are temporary, Hygiea is not. Not exactly permanent. Eventually, in the far future, the sun will expand and consume the inner planets, and the asteroid belt will be reshaped or destroyed, but on any timescale relevant to human existence, Hygiea is functionally eternal. It was there before us, it will be there after us, and it does not care whether we call it a dwarf planet or an asteroid or nothing at all, but we care. We care because naming things is how we make sense of the universe. We care because the categories we create shape the questions we ask, which shape the missions we fund, which shape the discoveries we make. If Hygiea is just an asteroid, it gets filed away in a catalogue and forgotten. If Hygiea is a dwarf planet, it becomes a target, a priority, a world worth visiting. And visiting it might tell us things we need to know. Not just about Hygiea, not just about the asteroid belt, but about the origin and distribution of water in the solar system, about the delivery of organic molecules to the early Earth, about the processes that built the planets we live on, about whether the ingredients for life are rare or common, about whether we are alone, or whether the universe is littered with the raw materials for biology, scattered by ancient collisions and delivered to young planets by the same violence that shaped the worlds between them. The answers are out there, in the dark, in the cold, in the silence of a sphere that was destroyed and remade 2 billion years before anyone existed to wonder about it. There is something else that the story of Hygiea reveals, and it is perhaps the most unsettling insight of all. It concerns the fragility of identity. When we speak of Hygiea, we speak as if it is a single continuous entity, as if the Hygiea that Annibale de Gasparis observed in 1849 is the same Hygiea that the spare instrument resolved in 2019, as if the Hygiea that orbits the Sun today is the same Hygiea that formed 4.5 billion years ago from the dust of the solar nebula. But it is not. The original Hygiea, the primordial body, the one that condensed from the nebula and orbited undisturbed for 2.5 billion years, is gone. It was destroyed, obliterated, reduced to a cloud of fragments that, for a brief period, hours, perhaps days, did not constitute a single object at all. There was no Hygiea during that interval. There was only a swarm, and then the swarm collapsed, and something new appeared. Something that inherited the mass, the composition, and the orbital elements of the original body, but not its structure, not its shape, not its surface, not its history. The Hygiea we observe today is, in the deepest sense, a different object from the Hygiea that was destroyed. It shares the same atoms, the same molecules, the same minerals, but those atoms have been rearranged. The structure is new, the surface is new, the shape is new. Is it the same world? This is the ship of Theseus, played out on a cosmic scale. If every part of an object is disassembled and then reassembled, is the result the same object or a new one? The ancient Greek philosophers debated this question using planks of wood. The asteroid belt debates it using fragments of rock and the force of gravity. In one sense, the answer does not matter. Hygiea is what it is, regardless of what we call it or how we classify its relationship to its predecessor. But in another sense, the answer matters profoundly because it forces us to confront the impermanence of everything. Every object in the solar system, every planet, every moon, every asteroid, every comet, exists in its current form only temporarily. Collisions reshape them, gravity remolds them, time erodes them. The solar system is not a static diorama, it is a dynamic system in which objects are constantly being created, destroyed, and remade. The worlds we see today are not the worlds that existed a billion years ago, and they are not the worlds that will exist a billion years from now. Earth itself has been catastrophically impacted. The moon, our moon, the one that hangs in our sky and shapes our tides and stabilizes our axial tilt, was almost certainly created by a collision between the proto-Earth and a Mars-sized body called Theia, roughly 4.5 billion years ago. That collision was, in many ways, similar to the one that created the Hygiea family, a high-velocity impact that shattered both bodies, created a cloud of debris, and resulted in the gravitational reassembly of two new objects, the Earth as we know it, and the Moon. We are, in a sense, living on a reassembled world. Our planet is a phoenix too, and if Earth is a phoenix, then Hygiea's story is not alien, it is familiar. It is our story, reflected in miniature in a dark sphere orbiting the Sun 3 times farther away than we are. The same physics, the same processes, the same cycle of destruction and rebirth. The only difference is scale. There is a passage from the physicist Richard Feynman that comes to mind here. Feynman once described the universe as a great chess game being played by the gods, with human scientists watching from the sidelines, trying to figure out the rules by observing the moves. We cannot touch the pieces. We cannot ask the players what they are doing. We can only watch and deduce and test our deductions against what we see next. Hygiea is one of those moves, a piece on the board that we did not expect to see where it is. Its roundness is a move that challenges our understanding of the rules, and the question we face is whether the rules are wrong or whether we simply did not understand them well enough. The honest answer, the one that makes the science more powerful, not weaker, is that we do not fully know. We have hypotheses, we have simulations, we have 170 years of observations, and a handful of stunning images from an adaptive optics system in the Chilean desert. But we do not have a spacecraft in orbit around Hygiea. We do not have samples of its material in a laboratory. We do not have a gravity map, a topographic survey, a seismic network, or any of the other tools that we would use to study a world that we took seriously. And until we do, the question of what Hygiea truly is, world or rock, dwarf planet or asteroid, phoenix or pretender, remains open. Open in the most literal sense, open to discovery, open to surprise, open to the possibility that the answer, when we finally get it, will be something no one predicted. That openness is not a weakness. It is the engine of science. The not knowing is what drives us forward. The gap between what we observe and what we understand is what fuels every mission, every observation, every late-night calculation. And Hygiea, sitting at the center of that gap, is one of the most compelling invitations in modern planetary science. An invitation to look, to go, to find out. The universe does not reveal its secrets to those who assume they already know the answers. It reveals them to those who are willing to be surprised. And there is one final dimension of the deeper truth that we must sit with, because it connects the story of Hygiea to the story of every human being who has ever looked up at the night sky and felt small. We are, all of us, made of the same material as Hygiea. The carbon in our DNA, the oxygen in our blood, the iron in our hemoglobin, the calcium in our bones. All of these elements were forged in the cores of massive stars that lived and died long before the solar system existed. When those stars exploded, as supernovae, as hypernovae, as cataclysmic detonations that outshone entire galaxies, they scattered their newly minted elements into the interstellar medium, the vast, tenuous gas that fills the space between the stars. Over millions of years, that enriched gas condensed into new clouds, new nebulae, new disks of spinning material. One of those disks became our solar system, and from the same batch of material, the same cloud of gas and dust, the same primordial mixture of hydrogen, helium, carbon, nitrogen, oxygen, silicon, iron, and all the rest, the Sun formed, the planets formed, the asteroids formed, and Hygiea formed. Every atom in your body was once in the same place as every atom in Hygiea, not the same general region, the same cloud, the same collapsing nebula. 4.5 billion years ago, you and Hygiea were the same thing, a swirling disk of gas and dust, indistinguishable, undifferentiated, sharing a common origin and a common fate. And then the disk fragmented. Some material fell inward and became the sun. Some material accreted into rocky bodies close to the sun, one of which became Earth. Some material drifted farther out, into the cold regions beyond the snow line, and became the primitive, carbon-rich, volatile-laden objects that populate the outer asteroid belt. You went one way, Hygiea went the other, and now, 4.5 billion years later, you are reading these words, or listening to them, and Hygiea is orbiting in silence, carrying the same primordial material that you carry, but untouched by biology, untouched by evolution, untouched by consciousness. It is, in a very real sense, the road not taken, the version of the solar system's raw material that was never given the chance to become alive. Or was it? We do not know what happens on the surfaces of C-type asteroids over billions of years. We do not know whether the organic molecules found in carbonaceous chondrite meteorites, amino acids, nucleobases, sugar-related compounds, represent the first tentative steps toward biochemistry, or merely the dead-end products of abiotic chemistry. We do not know whether liquid water, which may have existed briefly in the interior of the original Hygiea before it was destroyed, provided an environment where prebiotic reactions could occur. We do not know, and we will not know until we go and look. But the possibility is tantalizing. The possibility that Hygiea, or the original Hygiea, before the impact, contained environments where the chemistry of life could begin. Not life itself, not organisms, but the ingredients, the precursors, the first steps down a road that on Earth led to everything. If that possibility is real, then Hygiea is not just a world, it is a witness, a record of the chemical conditions that prevailed in the outer solar system 4.5 billion years ago, preserved in the form of minerals and molecules that have never been subjected to the geological recycling that erased Earth's earliest chemical history. Earth has plate tectonics. Earth has an atmosphere. Earth has oceans and weather and biology, all of which have continuously reprocessed the planet's surface material for billions of years. The record of Earth's earliest chemistry is gone, destroyed by the very processes that made Earth habitable. Hygiea has none of those processes. Its surface has been altered only by impacts, cosmic ray bombardment, and the slow effects of solar wind. Its interior, if any original material survived the catastrophic disruption and was incorporated into the reassembled body, may preserve chemical signatures that have been lost everywhere else in the inner solar system. Hygiea is a time capsule, and the message inside it might tell us something we cannot learn from any other source. This is why Hygiea matters. Not because of a label, not because of a classification vote, not because of the IAU's definition or the debate over what counts as a dwarf planet. Hygiea matters because it is a world that holds answers. Answers about the origin of water. Answers about the origin of organic chemistry. Answers about the processes that built the planets and delivered the ingredients for life. And answers about a catastrophic collision that destroyed a world and, from its ashes, created another one. Round, dark, patient, and waiting. The weight of that waiting is something we should not take lightly. Every year that passes without a mission to Hygiea is a year in which the questions remain unanswered. Every decade without a spacecraft flyby is a decade in which we rely on inference where observation would serve us better. The technology exists. The scientific case is clear. The object is there. 434 kilometers of reassembled rubble, silently circling the sun, carrying within it the memory of the solar system's most violent era. It asks nothing of us except that we come and look. And every time we choose not to look, we choose ignorance over knowledge, assumption over evidence, comfort over discovery. Science does not advance by waiting. It advances by going, by building machines and sending them into the void, by collecting photons and particles and fragments and bringing them home, by refusing to accept that the universe is unknowable simply because it is far away. Hygiea is far away, but it is not unknowable. It is merely unknown. And the difference between those two words is the entire history of exploration. We have come a long way tonight. From the quiet darkness of the outer asteroid belt to the conference halls of Prague, from the violent destruction of a world 2 billion years ago to the adaptive optics of a telescope in the Chilean desert, from the oldest questions in science, what are things? How do we classify them? To the newest discoveries that threaten to upend the answers. And through it all, one object has been at the centre of the story. A dark sphere, less than 500 kilometres across. An object so dim that it reflects barely 6% of the sunlight that touches it. An object that was shattered and remade, that carries the chemical fingerprints of the solar system's earliest era, that meets every criterion of a classification system designed to define what a world is. And that, despite all of this, has never been visited, never been touched, never been seen up close by human eyes or human machines. Hygiea's story is not just about Hygiea. It is about the way we draw lines, the way we separate the important from the unimportant, the worthy from the unworthy, the world from the rock. These are not just scientific distinctions. They are reflections of how we think about significance, about value, about what deserves our attention and what does not. When the IAU voted to define planet in 2006, they were not just resolving a scientific question. They were making a statement about priorities. Planets are the objects we study. Planets are the objects we send missions to. Planets are the objects we name our missions after, put in our textbooks, and teach to our children. By creating the category of dwarf planet and placing Pluto, Ceres, and a handful of others into it, the IAU was creating a hierarchy. At the top, the 8 planets. Below them, the dwarf planets. Below them, everything else. Hygiea challenges that hierarchy from the bottom. It sits among the everything else, the asteroids, the rubble, the debris, and calmly presents its credentials. It orbits the sun. It is round. It has not cleared its orbit. By the rules of the hierarchy, it belongs in the middle tier. And yet, for 20 years, it has been left in the lowest one. Not because it fails the criteria, but because no one looked closely enough to see that it meets them. How many other objects are in the same position? How many dark, cold, distant spheres orbit the sun in the outer belt, in the Kuiper belt, in the scattered disk, in the Oort cloud, round enough to qualify as worlds but too dim and too distant for anyone to check? The answer could be 0. It could be 500. We genuinely do not know. And the fact that we do not know, the fact that our census of worlds in the solar system is, by every measure, incomplete, is itself a profound statement about the state of our knowledge. We live in a solar system that we have barely explored. This is easy to forget. The images from Hubble, the photographs from Mars rovers, the data from Voyager and Cassini and New Horizons, all of these create an illusion of completeness. An illusion that we have seen everything worth seeing. But the truth is the opposite. The vast majority of the solar system, the outer belt, the Kuiper belt, the scattered disk, the inner Oort cloud, is virtually unexplored. We know more about the surface of Mars than we know about the population of objects in our own solar system. We have more detailed maps of Pluto's heart-shaped ice plain than we have of the shapes of the 1,000 largest asteroids. The lesson of Hygiea is that surprises lurk in the places we have not looked, that the universe is under no obligation to conform to our expectations, and that the most interesting objects are not always the brightest, or the closest, or the most photogenic. Sometimes, the most interesting object is the quiet one, the dark one, the one that has been sitting in our catalogues for 170 years, patiently waiting for someone to notice that it is round. What does this mean for the future of exploration? It means that we need to broaden our gaze. The era of studying only the most obvious targets, the bright planets, the large moons, the spectacular comets, is drawing to a close. The next era of solar system exploration will be defined by surveys, by wide-field telescopes that can image thousands of small bodies and determine their shapes, by infrared observatories that can measure compositions across the full spectrum, by missions designed not to visit one object but to characterize dozens or hundreds. The Vera C. Rubin Observatory, currently under construction in Chile, will begin its legacy survey of space and time in the coming years. Over the course of a decade, it will catalogue millions of solar system objects, measuring their brightness, colours, and motions with unprecedented precision. It will not directly resolve the shapes of small asteroids. Its resolution is not high enough for that, but it will identify the objects worth studying in detail. It will provide the target list for the next generation of adaptive optics observations, space telescope campaigns, and spacecraft missions. JWST, as we discussed, can provide compositional data for individual targets. The upcoming European Space Agency mission Hera, designed to study the Didymos-Dimorphos asteroid system in the wake of NASA's DART impact experiment, will provide new insights into the internal structures of rubble pile asteroids and concepts for future missions. Small, low-cost spacecraft using solar electric propulsion to tour multiple asteroids are being developed by teams in the United States, Europe, Japan, and China. Hygiea is not yet on any of these mission manifests, but the scientific case for visiting it grows stronger with every new analysis, every new simulation, every new debate about the boundary between a rock and a world. The 2019 SPARE results were a beginning, not an end. They opened a door that cannot be closed. And behind that door lies a solar system that is far stranger, far more populated, and far more interesting than the one we thought we knew. The great irony of the Hygiea story is that the most important question it raises has nothing to do with Hygiea itself. The most important question is, what else have we missed? What other objects are out there, in the darkness between the planets, carrying secrets that we cannot even imagine because we have never bothered to look? The history of astronomy is full of examples of discoveries that happened only because someone pointed a telescope at the wrong part of the sky, or analyzed data that was supposed to be useless, or followed up on an anomaly that everyone else had dismissed. Hygiea was an anomaly. For 170 years, it was dismissed. It was catalogued, measured, and filed away as just another asteroid. And then someone looked at it properly, and the anomaly turned out to be a world. The universe is full of anomalies. The question is whether we have the patience, the resources, and the humility to investigate them. And so we return to where we began, to the darkness between Mars and Jupiter, to the cold, the silence, and the patience of a sphere that has been orbiting the Sun for 2 billion years. Hygiea is not the largest object in the asteroid belt. It is not the brightest, not the most visited, not the most famous. It does not have rings or moons or atmosphere. It does not have a heart-shaped glacier or a volcanic surface or a giant red spot. It does not appear in textbooks. It does not appear in science fiction. If you mentioned its name at a dinner party, most people would not know what you were talking about. But Hygiea is round. That single fact, that one geometric property, measurable in pixels on a detector in the Chilean desert, has quietly overturned 170 years of assumptions. It has challenged the definition that governs what we call a world. It has forced planetary scientists to reconsider the relationship between size and shape, between violence and order, between destruction and creation. And it has opened a door onto a solar system that may contain far more worlds than we ever imagined. The question the title asks is simple. Is Hygiea a dwarf planet? And the answer, based on the evidence available today, is this. By every criterion in the definition adopted by the International Astronomical Union in 2006, Hygiea qualifies. It orbits the Sun. It has not cleared its orbital neighborhood. It is not a satellite. And its shape, as measured by the SPARE instrument on the Very Large Telescope, is consistent with hydrostatic equilibrium. It is round as Ceres, which already holds the title, as round as any dwarf planet in the catalogue. But the formal reclassification has not happened, and it may not happen for years or decades, because the IAU moves slowly, because the definition is imperfect, because the politics of classification are complicated, and because astronomers are, understandably, reluctant to reopen a debate that once consumed far more energy than any scientific question should. In the end, though, the label is the least important part of the story. What matters is what Hygiea represents. It represents the persistence of gravity, the force that, given enough mass and enough time, always finds the sphere. It represents the resilience of matter, the fact that a world can be completely destroyed, shattered into thousands of fragments, and still reconstitute itself into something round, something ordered, something that looks, from a distance, like a world that was never touched. It represents the incompleteness of our knowledge, the humbling realization that one of the largest objects in the asteroid belt, an object we have known about since 1849, was hiding a secret in plain sight for 170 years. And it represents a question that we have been circling throughout this entire journey, approaching from different angles, examining through different lenses, but never quite pinning down. The question is not, what is Hygiea? The question is, what is a world? A world is not defined by its size. There are worlds smaller than some moons. A world is not defined by its atmosphere. There are worlds with no atmosphere at all. A world is not defined by its habitability. Most worlds are uninhabitable. A world in the deepest sense is defined by what gravity has done to it, by whether the forces that shape it from within have overcome the forces that preserve its randomness, by whether it has crossed the threshold, that invisible line between chaos and order, where the pull of its own mass has imposed a shape that no external force could create. A sphere, the simplest and most profound shape in nature. Hygiea crossed that threshold, not gently, not gradually, not through the slow, patient work of geological time. It crossed it through violence, through the most extreme event that can happen to a solid body, total disruption, and through the equally extreme event that followed, total reassembly. It was destroyed and remade, and in the remaking, it found the shape that defines a world. If the sun were a basketball sitting in a park in Cairo, Hygiea would be a grain of fine sand, roughly 400 meters away. You could walk past it without noticing. You could step on it without feeling it. It is that small, that insignificant, by the scale of the solar system. And yet, that grain of sand is round. That grain of sand was destroyed and rebuilt by the same force that shapes stars and galaxies. That grain of sand may contain water, organic molecules, and the chemical precursors to life. That grain of sand has been orbiting the sun since before multicellular life existed on Earth. And we have never been to see it. The night sky is full of things we have never been to see. Full of worlds we have never named, never classified, never visited. Full of spheres of rock and ice, drifting in the darkness, each one a story, each one a mystery, each one a piece of the puzzle that is our solar system's history. Hygiea is just one of them, but it is the one that stepped into the light, the one that forced us to look, the one that, through the simple act of being round, asked us a question we could not ignore. And so tonight, as the story ends and silence settles, consider this. Somewhere between Mars and Jupiter, right now, at this very moment, a dark sphere of ancient rock is making its slow circuit around the sun. It does not know it is being discussed. It does not know it has been measured and debated and argued over. It does not know that its shape, the quiet perfection of a sphere, has challenged the way an entire species thinks about the meaning of a world. It simply orbits, as it has for 2 billion years, as it will for billions more. Round, dark, cold and patient. A world that was destroyed and reborn. A world that nobody talks about, until now.